Hi, this is a makeup lecture from this week. I'd like to begin by reviewing the important educational objectives of Lab 8, and there were quite a few. The biggest one was this issue of sampling, okay? And the sampling or data acquisition involved starting with a transducer, which was a slide pot, and we hooked this up to the A to D converter, and the transducer converted the distance to a resistance. Okay? And then the circuit converted the resistance back to a voltage. Okay? And that voltage was somewhere between 0 and 3.3 volts. And the distance was 0 to approximately 1.5 centimeters. Okay? And now the A to D converter converted that analog voltage to a digital number, 0 to 4095. Okay? A number. The next step in our sampling was the calibration or the conversion of the number to a fixed point value. And so this integer that we calculated, which was the integer part of this distance, went from 0 to approximately 150. Okay? And then our last step was to output the number onto the LCD, okay? 0.00 centimeters up to 1.50 centimeters. Okay? And this sampling process involved all of these. But there was one more important component of this sampling, and that is we sampled at a periodic rate. Okay? We sampled at a rate of 60 hertz. 60 times a second. We did this process. And once we do that, we can invoke the Nyquist theorem. The Nyquist theorem, which says once we do that, we are successfully representing all the frequencies from 0, which is DC, up to, but not including 1/2 Fs. In our case, 1/2 Fs was 30 hertz. Okay? So that's the information encoded in that. And the way we did it was to use a cystic interrupt. So we had a 60 hertz cystic interrupt. And that interrupt was invoked every 16.6667 milliseconds. Okay? That's how often it happened. And what we did is we sampled the A to D converter. Okay? But if you remember, in previous labs, we had a heartbeat. And we could add a heartbeat to this as well. We could add a heartbeat. And so if we were to toggle PF1 3 times, it's called triple toggle. So in the interrupt service routine, we toggled this bit 3 times. The other aspect of, and I'll show you what that looks like in a minute. The other aspect of this interrupt is we set a flag right here. And this flag is called a semaphore. The combination of this global variable, both data and flag are global variables, but the data and flag together we categorized as a mailbox. Right? And if the flag was equal to 1, that means there is data. And if the flag is equal to 0, that means no data, and we'll see this in a second. Okay? The other linkage of my system is the main program. And the main program is going to basically look for the flag. And if the flag is equal to 0, that means there is no data. So it will wait. And if the flag is equal to 1, that means there is data. And so what I will do now is to convert. Right? I will go convert the data that I captured here into a distance. Right? This distance here is my distance parameter. And then output it as a fixed point value. Okay, we did that in the last lab. And then when I'm done, I'm going to set the flag back to 0 again. In this, you can see the mailbox is basically allows me to synchronize this foreground, this background thread here, this interrupt here, this interrupt thread, and this main thread over here. So the main thread and the background thread are connected. All right. So that was the essence of sampling. Okay. The other things we had is we had calibration, which occurred in here, and we had we talked about noise. Let me zoom into this part of my debugging here and look at what happens when I hook up PF1 to the scope. Okay, so all right. If I were to zoom way in, and let me just give it to you again here. So my interrupt service routine, toggled PF1, toggled PF1, sampled the A to D converter, set the flag, and then toggled it a third time. This is called a triple toggle debugging technique. Okay. Triple toggle technique. All right. And so if I looked at PF1 on my scope or logic analyzer, I would see the first two toggles would occur very close to each other. This is toggle number 1, and that's toggle number 2. And they're going to be separated by about 80 nanoseconds because that's how long it takes to toggle. But the interesting one is here, between the second and the third, okay, which is going to be about 10 microseconds, by the way, is going to be the time it takes to execute this line code. So if I zoom into this PF1, I can see, yes, an interrupt has happened because there's 3 toggles, but I can also see that the time to execute this interrupt service routine is about 10 microseconds. We're not done. So let's zoom out in time. This was a zoom in. Let's zoom out. And now let's look this on the millisecond range. Now, if this toggles 3 times, it turns out when I do this in the millisecond range, the 3 toggles are going to be right on top of each other and look like one toggle. Okay? But now, this is the same PF1. I'm just now going to change the units. This was in microseconds. Now I'm going to go to milliseconds. And I will see that 6.667 millisecond interval here. And another 16.667 milliseconds there. Okay? So if I zoom out, I can see the time between interrupts. So the time from 1 to 1 is the time between interrupts. And that is going to be exactly 1 over 1/60th of a second. Okay? In this, using a toggling pin and an oscilloscope, so I can see where my software is running. 1, 2, 3 means I'm in the interrupt service routine. And when, okay, I know where it is because it's toggling. I know when it is because I can see it versus time on my scope. In this combination of where is my software and when is it is called a profile. Okay, so this is a software technique called profiling. All right, there we go. All right, so that's what I wanted to say about Lab 8. Let's go on to Lab 9. Okay. All right. The essence of Lab 9 is that we're going to communicate. Okay. And so what we're going to do is we're going to take the slide pot on this computer, basically create an entire data acquisition. The A to D converter, the convert, all that. But rather than display it on this LCD, we're going to transmit it to another microcontroller and then output it on that LCD. Okay? So the distance here is going to show up on this LED distance there. Right? But we're not, and this is a second microcontroller. So this is a TM4C 123. This is a TM4C 123. But we're going to have data in the other direction. There's going to be a slide pod on this one. Okay? And it's going to have its own distance, and it's going to go to its own A to D converter. Okay? In its own convert. And we're going to send data in the other direction. And it's going to show up on this LCD right there. Okay? It's going to show up on this LCD. So this distance here is going to show up over there on that LCD. And in order to do this, we're going to have to communicate. And communication in this particular lab is going to be centered around the universal asynchronous receiver transmitter. And there's going to be one right here and one right there. It's built into the TM4C 123. This universal asynchronous receiver transmitter. It turns out the grounds are going to be connected. And so you're going to see 3 wires here in this cable. One for sending data from left to right, and a second wire from sending data right to left in this essence of serial, which means 1 bit at a time. And so what we're going to see is that in order to communicate, what we're going to have to do is first encode this information. Right? So we're going to take distance and encode it. Okay? And that is change it until we get to physics. We're going to encode it. We're going to have little energy packets. And these energy packets are going to transmit across space. And then we're going to have to decode it, convert the energy back into numbers, back into distance again. Okay? And this is the process of communication. Now, we're going to do this 1 bit at a time. We're going to see there's going to be a message. We're going to create these are now going to be packets. These are going to be bytes. Okay? And we're going to have a message. And it's going to begin with an STX, which is hex 2. Then we're going to send the first digit, which is the ones digit. Right, so that's going to be a 0x30. Probably only go to 31. And then we're going to send the decimal point, which is a 0x2e. Then we're going to send the 10th digit, which is going to be encoded in ASCII as a 30 through 39. And we're going to send the hundredths digit, another 30 through 39. We're going to send a space, which is a 20. We're going to send a carriage return, and 0x0d, that's a 13. These are each bytes, and we got one more. We got an end of transmission, okay, which is going to be a 0x03. And so we see that we are going to have 8 bytes. Okay, and in the next lecture, we'll zoom down in and tell you how we send the bits. But here in this lecture, we're going to see that we're going to encode the distance as 8 bytes of information in ASCII, such that we see the ones digit, the decimal point, the 10th digit, 100th digit, followed by a couple of spatial characters. And we're going to use 8 bytes because it'll be very easy on the other side to generate an interrupt on the UART when it receives 8 bytes. So we're going to get an interrupt at this point on the receiver when it gets this entire message. Okay. All right, so this is a brief introduction to Lab 9. When we come back next time, we're going to talk about how the UART works. We'll zoom into this particular protocol and show how these 8 bits of each of these bytes is communicated. What does it look like on the wire, etc. Anyway, go ahead and look at the PowerPoints 11 and 12, and we'll see you on Thursday. All right, bye.